Well, good morning, everyone. I'm Larry Olson with Olson Engineering, President and Founder, and it's our pleasure to be giving you this webinar today. We did a lot of webinars during the pandemic, and we've decided to start giving webinars again on a monthly basis. So if you're interested, you'll be seeing notices that basically the last Thursday in each month at this time, we will be giving another webinar. It'll be either on geophysics or non-destructive evaluation, our specialties here at Olson Engineering. And many of you know we also have a subsidiary company, Olson Instruments, that sells some specialized non-destructive evaluation and seismic downhole and crosshole geophysics testing equipment. So with that, my co-presenter today will be Jared Lowe, Senior Project Geophysicist. Jared's been with us for over 3 years now as a bachelor's and master's in geophysical engineering and then geophysics master's from the Colorado School of Mines. He did his research in his master's on archaeological ground penetrating radar down in a historic South American site. But we're not talking about ground penetrating radar today. We'll be focused on electrical resistivity imaging of sites and aging, a little uniquely mechanically stabilized earth walls for corrosion service life evaluation. I'll be speaking to that. I've personally done electrical resistivity. I think you'll find Jared's portion of the talk very interesting, give you some good background and case histories. So with that, I want to thank everybody who's joined so far. We'll go ahead and kind of get started. We had a pretty good sign up of around 160 people, but about a quarter of you are there so far. So we appreciate those that have been right on time and joined us. So a little bit on the history. I started Olson Engineering in 1985, always with a focus on imaging infrastructure, as it says, and structures for assessment, monitoring, repairs with non-destructive evaluation and geophysics. Olson Instruments first instrument was sold in 1993. It's a subsidiary of Olson Engineering. It manufactures instruments for testing concrete, asphalt, masonry, and wood materials and structures, as it says, pavements and foundations, and crosshole and downhole seismic systems. Our main office is here in Wheat Ridge, Colorado, which is metro on the west side of Denver, close to Golden. And we have a branch office in Rockville, Maryland, where we have 2 people out there, Wade Martin and Lindsay Hazelwood, that both have masters in geology and geophysics. And so we're servicing on a consulting basis the United States and international projects as well, frequently working up in Canada. So we have registered professional engineers in over 30 states, and Lindsay Hazelwood in our Rockville office is a certified professional geologist. So our consulting services are listed. I won't read them all, but I think you can look through that. We've done load tests. People don't often know that. We've talked about it in the past in one of our webinars. We'll probably update it. But for structural health monitoring of bridges and buildings, also vibration monitoring, the geophysics, as it says, for engineering, environmental, and groundwater, and the whole range of non-destructive evaluation services, working on dams, buildings, bridges, foundations, pavements, tunnels, virtually any kinds of infrastructure. I will mention that we have a training seminar coming up. We're doing this every 3 days, an Olson Instruments class each year. And we also teach courses. I'll be teaching one next week for ASCE on concrete and masonry, part of structural condition assessment of existing structures in Miami. Also teach ASCE bridge condition assessment courses, and I've taught on concrete dam inspections and repairs, as well as on concrete dam assessment and embankment dams as well with non-destructive evaluation and geophysics. So this is the information on the webinar, the users seminar. We call it our NDE in Geophysics User Seminar. It'll be March 3rd through the 5th at our office here in Wheat Ridge, Colorado, and we are also broadcasting it virtually. There's an option to attend it that way. It's basically covering structures the first day, foundations and pavements, and then geophysics on the last day. So we have live demonstrations. We're giving out 7.5 PDH hours for each day of attendance. And starting at 8:30 and ending at 5. And you can register by emailing seminars@olsoninstruments.com. And you can also go check out on our website the previous webinars we've given. We'll post this one within a couple of weeks up there as well. Okay. And with that, This is the outline of where we're going today. I'll just go through this and then Jared will take over the presentation. But we're going to go over outcomes and some applications. What do you measure it in electrical resistivity, concepts, types of surveys, instrumentation, and many case history examples. And finishing with talking about the mechanically stabilized earth wall resistivity, and I'll join in again with the corrosion evaluation. So that here is Jared Lowe.
Yeah, and nice to meet you all. So yeah, getting started, we'll go through some common terminology.
And discovers the
Yeah, let
best
me
remains.
just try to keep yourselves muted for this until we have questions at the end. Yeah, so electrical resistivity tomography is maybe the more common terminology for this. It's also known as ERI or resistivity imaging. And then the 1D case of it would be vertical electrical sounding, VES. And this is more commonly used for, individual sounding locations at a single point, typically for grounding surveys. And then lastly, throughout all of this, we have, your physics 1 concepts of V equals IR, Ohm's law, and we're using this concept to ultimately generate a resistivity model of the surface, subsurface by using earth as a resistor and inputting a current and measuring a voltage drop. So the ultimate outcome of resistivity is to generate that 2D subsurface model. You can see we did 6 lines on the right, the top right here. And so, yeah, we get against a linear distance, we have resistivity with depth. And this is 6 lines in Idaho, ultimately getting layered models of the subsurface. Similarly, from the same site, we have a 1D VES sounding, where we ultimately get similar results. And then you can extend this to 3D and 4D, doing sort of combinations of linear arrays to cleverly get 3D maps, or doing time-lapse arrays to get 4D maps, where you sort of take time samples throughout the year to compare them to each other. Common applications would be for groundwater, locating, conductive zones where you would normally see groundwater, or just simply anomalies. So seepage zones, caves, sinkholes, general void spaces are common applications for resistivity. In a more formal sense, engineering sense, you use your 1D surveys, VES, for grounding design. And we've been doing some work with corrosion assessment. And that's going to be the ultimate goal of this presentation once we get through a little bit more background on resistivity. So again, we're using the basic concept of Ohm's law, inputting a known current, measuring a voltage drop across different electrodes in the ground, and ultimately backtracking out a resistance. It comes to resistivity by taking resistance across a known distance, because when you sort of survey across, Earth, I think that becomes a much more important aspect of it. So we'll be talking in terms of resistivity for the rest of the presentation. So here's your common setup. This is with just 4 electrodes. You have a pair of current injection and current sink electrodes, which your current flow path flows along. And then you would have 2 voltage drop electrodes in the middle between the 2, typically. You can get really creative with where you put these potential electrodes to maybe survey, different sensitivities of the subsurface. But that's the general setup. So again, going from resistance to resistivity, we need to have an sort of concept of, okay, where's the current actually going through the ground? And so we need to have what we call a geometric factor, and that's very important for backtracking out resistivity, the true model of resistivity of the subsurface. So here is an example case where we have equal spacing for all of them, but we have AM, AN, NB, MB. These are the common sort of connotations or letters associated with current injection and potential electrodes. So on the bottom here, you can see the general equation for mapping out the geometric factor. And then on the bottom right, we have the estimation for apparent resistivity, which is what we use. Given a geometric factor, we convert it to apparent resistivity using this geometric factor. But yeah, ultimately this is a 3D concept. Of course, current doesn't just go between the electrodes, it sort of radiates outwards when you inject it into the ground or any material. And so that's how we can get up to a 3D sort of idea. You can either do a full grid of electrodes and pulsing each one and seeing what voltage drops we get, or you can do what we call a pseudo 2D map, where we combine multiple normal 2D lines and then process them as a 3D body. And then lastly, as I mentioned before, you can do time-lapse surveys, potentially, okay, what is the groundwater level in the spring versus, the groundwater level in the summer? And that could be interesting for whatever applications. So there's many types of resistivity arrays. These are a couple, classic example ones that are implemented in the field, each of them having their own sensitivities, which I'll show on a different slide. But on the left, I just want to emphasize that you bring in the geometric factor again to calculate this apparent resistivity. And it often simplifies for different array types. So sensitivity-wise, you want to choose the right array type for your objective that you're trying to get at. So here's a couple sensitivities. Commonly used is the dipole-dipole array and the Wenner array. The dipole-dipole array may be more interesting to find laterally variable features such as dikes or faults. And then the Wenner array would be more useful for finding layered features such as groundwater tables or bedrock. So going on to sort of the 1D versus 2D versus 3D cases, this is how we would apply it in the field for a 1D case. We choose a center point. This would be between the M and N electrodes. And then we move out our M and N electrodes and our current injection electrodes to get deeper material or deeper sampling of material. So the relationship there is the longer your line length, the deeper you'll be able to go. Of course, this is with limitations to the strength of your system, the strength of the current that you're injecting, as well as just the geology, how conductive the material is, offers insight into how deep you'll actually be able to survey. And the bottom right here is the final result. You would get a 1D plot of your resistivity versus depth. So instrumentation wise, this can be as simple as just having a multimeter with some current injection. Land mapper here is a little handheld system, and so it has terminals at the top. And all you have to do is stick electrodes in the ground and press the button, and it'll start giving you resistivity readings. Of course, that's with knowledge of how far your electrodes are. This goes up to a bigger case when you're doing 2D. Basically, this is a switch box that controls which electrode pairs you're actually running at the same time. So we have an array here of 84 electrodes, and what this switch box and controller does is it just switches between each of them following whatever array type we want. So dipole, dipole, Wenner, gradient. And typically you can program these so that you can run multiple at a time to get a full image, including the sensitivities that you want. So here's a GIF I found that's somewhat useful in showing, okay, here's your current injection, what depths you might be sampling, and what you'll actually be seeing in the field. Most instruments have a digital display where you can see a pseudo section. And this basically just displays, okay, what's the resistance, or if it has information on the geometric factor, what's the resistivity that you're returning when you take the current injection and voltage drop. So here's another image just showing, okay, here's some of the values, and this is just an estimate in the field. This can help with seeing if there's any metallic features that you should maybe consider or remove before getting back to the office to process data. Another interesting application of 2D resistivity, you can actually tow these systems or place them along ocean bottoms or river bottoms to get better information of that subsurface. We've not been able to do this yet, but AGI has a lot of support for marine surveys, and this offers just another way to look through river bottoms. Yeah, as I mentioned before, this is sort of your 3D idea where you have one current injection electrode and multiple voltage drops between a whole set of electrodes. And this lets you get high resolution data for a given, a given survey area. This would be a very low resolution image, but image of that one of those 3D surveys being collected. Similarly to 3D, you can make your pseudo 2D, 2.5D, which would be combining a bunch of 2D lines. This is an example for archaeology, it's where it's commonly done. So you have in the bottom left image here, you have four fixed space electrodes. And so with this, you'll have one geometric factor and you'll be going one certain depth. And so you just drag this system along and you get ultimately a conductivity map of that depth for your entire area. This could similarly be done with electromagnetics, but it's often the case that you could, choose a specific depth that you want with this system and then, run this exact depth throughout the entire area. Whereas with electromagnetics, you might not be able to go as deep as with resistivity. So yeah, data processing wise, I've been harping on the fact that, yeah, you measure resistance based on a current injection and voltage drop. You calculate apparent resistivity based on geometric factor, but ultimately we want to come out with a modeled resistivity of the subsurface. People usually call that modeled resistivity, but you ultimately want the true resistivity, and that would be the resistivity of those exact materials. So here's the workflow of it. You start out with an initial Earth model, be it like a one layer model or a two-layer model. You choose a resistivity that you think might be representative for your geologic area. And you say, okay, what if we put electrodes exactly as we did with our survey into the subsurface? How does that match the field data that we see? If it doesn't match at all, then we go back, we iterate, we try a different model, and then we keep on iterating until our field data is basically replicated by this model. And so we have a set of criteria that we choose in order to say, okay, stop iterating, and we'll accept this model. Then there's a lot of parameters that we can tweak into here that I won't go into in this presentation, but ultimately the outcome would be a resistivity model. So here is an example of that. In the middle here, we have interpretations for soil and a bedrock layer, where your bedrock layer may have a higher resistivity. And then your y-axis here is depth. Similarly, on the right plot, we have our x-axis is depth instead, and our y is resistivity, often plotted in log scale. Depth, I like to plot it in linear, but as we can see in the middle one, that one's log. And then similarly, there's a similar process for the 2D case. However, this gets a lot more complicated, adding in a second dimension of, this x-axis where, okay, now we have a lot more potential resistivities to try out. So when we think about trying to do it in a 2D case, we break it into voxels or blocks, where we have a finer, more discrete model towards the top and looser towards the bottom. This is based on the idea of sensitivity of just the array. So you're a lot more sensitive to data at the surface because you have more coverage. So your ray paths of your current through the subsurface hit these very top soils way more often than you'll be able to get these data towards the bottom. That's why you also see this trapezoidal shape. You won't have current injection over here or voltage drop information over here. So typically people crop the data so that we're not extrapolating anything outside of that trapezoid. So this is just showing again, if we have our pseudo section, we can ultimately calculate what we think the subsurface looks like. So if we were to put probes into this top layer model, we would ultimately get out this middle plot, which is very similar to the resistivity that we saw in the field. And then a last step in processing that's very important is adding in topography. So in this plot, I'm not sure if this was blue as conductive or red as conductive, but either way, once you add in topography, you can see that this giant blue blob ends up just showing that, okay, maybe it's just a pile of dirt or looser material that covers maybe your normal bedrock. And you wouldn't have seen that without adding in topographic information. So going on to interpretation, here is a plot of general information for, say, soils, where you have conductive clays showing up as low resistivity values. Of course, conductivity being the inverse of resistivity. I maybe should have mentioned that earlier, but and then you transition to more resistive gravels. So this is a way to sort of get information about maybe what might be below your subsurface. Here's some more potential minimums and maximums for different materials. But it is important to note that there's a lot of overlap between these materials. So resistivity is not a one-shot method for determining, okay, is this a shale bedrock or a sandstone bedrock? Because of course these mins and maxes overlap a ton. Factors that are affecting resistivity or conductivity, of course, with more soil moisture, you might have a more conductive material. So, groundwater through the subsurface often has dissolved ions, resulting in more conductive readings. And similar with clay content, for those in Colorado that are familiar with GPR, I think it's very commonly known that clays are very conductive and often attenuate GPR signals, and that's a similar case for resistivity. So yeah, we can get started into some of the case studies. This is an example of doing a resistivity survey. I believe red is more conductive. So we have this red conductive anomaly in the center of our survey, and that we associated with a mud-filled karst, or a mud-filled area within karst limestone, which may have previously been a void that maybe people were concerned about. Another survey that we did was in the mountains of Colorado. This is your sort of pseudo 2.5D, 3D plot where we did 8 lines across this mountainside, looking for sort of the extent of the tailings pile, as well as just maybe where the bottom, where we would see bedrock. So we have this resistive, very loose material towards the surface in red, as you can see in the inverted resistivity section at the top, covering the tailings pile, which maybe is more conductive below it. Of course, there's a lot of noise within that tailings pile just based on loose metals, etc., that's been left there, as well as minerals that maybe weren't fully extracted from those rocks. Another case you can use it a lot for is landfills, where you might be having these contaminant plumes. Similar to electromagnetics, electrical resistivity is very sensitive to conductive bodies. So that's what they were looking for in this project. And then lastly, I want to show an archaeological example. So this is at one given depth using that ohm mapper system with fixed electrodes. They just drove it across this entire area to map out anomalies. And this could similarly be done with GPR electromagnetics, but this is very useful for getting a given depth that may be deeper than what you can get with GPR. So this is the case study that we wanted to focus on for this presentation, which we did along these MSE walls, mechanically stabilized earth walls. And these have these strips that go into the roadway to help hold up walls that extend onto, extend like off ramps and on ramps, typically to bridges. And so on the bottom left here, we had a client that was experiencing heavy rusting due to the application of de-icing salts onto the roadways. And so as they were, pulling up some stuff to install a new drainage pipe on the side here, yeah, they were encountering these completely rusted out strips, which would not be good for holding up the entire, 30-foot wall. And so on the right, here's the design of the wall. You can see these MSE panels, as well as very faintly, you might be able to see blue, green, yellow, and red. We did 4 lines along the bottom of this wall that we could access by foot. So the DOTs require for backfill a 30 ohm meter and higher resistivity requirement. On the bottom here, you can see some of the criteria and resistivity being one of them. So our thought we could bring in resistivity as a method, put them into the wall and test, okay, what's the backfill looking like in today's standards? Because they may have put in high resistivity material at the start, but with all these de-icing salts, that material might be changing and the lifetime of these straps will reduce. So I've assigned a color code here, red being more corrosive, just based on this 30 ohm meter criteria. And so we'll see this color code in the future plots. So here's a couple images of the surveys that we did, and you can see the same MSE panels that were in the drawing. So we did a survey at 3.5 feet off the ground, just above this little barrier, sticking them into the joints. We had to have somebody jackhammer out little holes for us in case of the joints were a little too tight. But yeah, we did this every 10 feet. Luckily, the panels were every 10 feet, I believe. And we had the guys bring a lift out to help with some of the higher up points above the brush over here in the left image. This was done with a AGI Super Sting that you can see on the right here, controlling 84 electrodes that go through the whole MSE wall. So this is the first plot. This is looking top down. This is satellite imagery of sort of, yeah, so top down, and then you have your electrodes in the wall. So we're able to see the full pseudo-section just overlaid here. And this is the survey from 3.5 feet, fully inverted. And then I threw in a contour at 30 ohm meters, just for interpretation's sake. I would like to note further towards the median of the road, we have what we would interpret as very corrosive material as seen in red and orange closer to the road. However, I would like to note that this is an interesting use case for resistivity, where we have basically like an air void above us, which is the top of the road. So when you're interpreting this, it's very important to, keep in mind that you have this air void that might be causing sort of artifacts in your data. And I believe that towards the median, that data might not quite be real because, you have this air void affecting your model. And we see that in general, most of the rest of the data is within this 30 contour, at least on the right side. So you should be able to extend that sort of information towards the deeper side. The other factor here is that the MSE strap should only be going, I think, 20 feet into the wall. So we're not caring too much about information past that. Similarly, here's our 8.5 foot above grade survey that was inside of the wall, and we got pretty repeatable results between the two, not too different. And then lastly, we did another survey from the top down to get a little bit of information at the top because we weren't able to get electrodes way up at the top of the MSE wall. These are just points colored by GPS. So we have higher elevation on the left side towards the bridge, and then we get lower elevation on the right. And we had the same 84 electrode system used at the top. So we have the same case here. This is the data overlaid on top of the drawings of the MSE walls. We can see lower towards the bottom, we have the same artifact of, okay, we have our survey only 9 feet from the edge of the MSE wall. I believe we're getting a strong effect of, just having an air void directly next to our survey. But we are trying to get information of that more top material. And I think we succeeded there, where you can see on this bottom plot a little bit better. We have at the very tops of the soils, we have a much more resistive medium before getting to, much more conductive medium, red, relating to more corrosive material, compared to deeper where it might be more sound. So I'm going to pass it back to Larry to talk about our estimations for using that corrosive data for lifespan left within these strips.
Okay, thank you, Jared. This was our second project. We'd earlier looked at 7 walls with similar resistivity methods to predict remaining service life. Um, One thing I'll mention and back up just a bit as a preface to this, that when they first discovered that they had some concerns about the corrosion of the zinc-coated galvanized strips, which were the standard strips, non-lead 50 millimeters by 4 millimeters with a zinc coating. And they did it, as in any wall, the uh, deeper down you are, the longer the strips go back into it. But this was right at the top, and here they've found the corrosion. So at that, before we got involved in the project, they'd done some additional testing. I'm not showing those results, but they also looked at not only the laboratory resistivity, which when you do this type of testing initially on the backfill soils, you saturate them, do a laboratory test, and get the lowest resistivity to find out the most corrosive conditions, assuming it could become saturated in the future. But they also tested for pH of the existing soils. They'd done some limited laboratory resistivity tests of the backfill soils when they excavated them. And this was over about 30 years later that this occurred. And they found some pH problems. It was out of the range, and there's obviously pHs that are more lower or more acidic, leading to corrosion of the zinc, and it serves as a sacrificial protection layer. The chlorides, they also found problems with chlorides and sulfates. The organics were fine, but these are the criteria that the Department of Transportation or MSE wall designers will look at to say this is what the properties of the backfill soil should be. So what I'm indicating is that laboratory testing, in addition to the resistivity work we did, indicated there were some areas that were more corrosive to very corrosive. And so when you drop from the 3,000 ohm centimeters or 30 ohm meters, as we reported it, below that is when you get to moderately corrosive to very corrosive. And we found some areas with that. So with that as a bit of a preface to what I'm going to talk about is we took this information, and this was a reinforced earth company wall, and they did have the design drawings and records, if you will, for the wall, which is very helpful. And as part of all this, the zinc coating loss from RICOs, and I'll refer to Reinforced Earth Company as RICO, uh, for 2 years, it's like 15 micrometers per year, and you lose 30 micrometers. So with the typical zinc coating, calculating the years it takes to get to the steel that it's protecting and for the zinc to be corroded away, you start off with this 86 micrometers times 2 times that, because you have two sides to your zinc strip that are corroding, and divided by this 4 micrometers per year, plus 2 years for the initial zinc coating loss. One comes up with 16 years before the zinc would be corroded in this case. And this is assuming it's right at this 3,000 ohm centimeter, 30 ohm meter level. So the strip steel loss then becomes the number of years times 12 micrometers per year after that. And so that's the actual steel rate that RICO has come forward with as their part of their design assumptions and from their many years of experience in this area. The company has been renamed in the last couple of years. You'd have to look up Reinforced Earth Company to find the new name of it, but they're still going strong. So the design stress, two approaches were taken. The structural engineers want us to look at it. Well, let's look at it from a design stress perspective, which it was the initial design and has some safety factors in it, and then versus a yield stress for the strips when it would have lost so much section that it would begin to yield and in essence be a failure. So for that wall, this, the maximum reinforcement tension expressed as FT is equal to this yield stress of 65 KSI times the safety factor 0.55 times the area of the strip. Well, I shouldn't have said safety factor, but in any case, that's reducing it to a safe stress level. So it is a safety factor in that sense. It's the design allowable stress. So So the strip gross area, you look at that, it's 4 millimeters times 50 millimeters. Converting that is 0.31 square inches. And the 65 KSI is 65 kips or 65,000 pounds per square inch for the yield stress. So the strip net area then, it's a half-inch little conservative diameter bolted tie strip panel connections where they literally tie the strips to these bolted connections. That comes out to be 0.22 square inches. But so if you apply that as being the most conservative point with the loss of section, et cetera, for a gross area strip yield stress, design stress calculation, you end up with 6.2 kips, which is equal to 65 KSI times the minimum area of the strip. So when you solve for the minimum area at the end of the service life, you would want to have left 0.173 square inches. So it would have dropped from the 0.31 to 0.173, or nominally 55%. So the yield stress is the failure with no safety factor. So applying these equations, then solving for that, you come up with, well, it won't start yielding until it loses about half of that amount again at 0.095 square inches. That would be the ultimate strength in a sense when it yields. So we went through those calculations to continue towards the results. I'm sure it's hard to see all this. I'll boil it down to be a little simpler, but we looked at different backfill corrosion aggressiveness states. As indicated earlier, based on the resistivity values, of very corrosive to moderately corrosive, in this case, cutting it off at 3,000 ohm centimeters, in other words, below that, and mildly corrosive as it got higher to non-corrosive. And that would be 5,000 ohm centimeters and even higher at non-corrosive. So the calculation then says, if we look at the first column, the years, second column over, for the design stress strip section to corrode from 0.31, the gross area to 0.173, the minimum area to 75-year service life in square inches. This is coming up with, if it was a zone where the backfill soils were now very corrosive, it would be 47 years. And it would be 59 years for corrosive to moderately corrosive case, 73.7. So taking into account the approximate year and having been built around 1996, the years were predicted to range from 2051 to 2086 in moderately corrosive areas. So 75 years out would put you basically, being in 1996, you would be at 2071. So there are concerns if you had a lot of very corrosive zones that about the service life. The next part is to corrode down to the minimum area, meaning to get down to this 0.173 inch at 75 years service life. And so we've gone through that. And if we get to the yield stress, let's just jump ahead a little bit to the right, since that's the one, it's the ultimate failure. Then you can see that even in very corrosive areas, it would have been 74 years and it would have met the service life here at 2078. So it was showing that there was cause for concern, but in the worst case of getting to yield stress, it still should perform over the service life. And those years are predicted there at the right of approximate years to failure as well. Obviously, it's much sooner here with it coming in at 2047 versus 2061. So we went one step further, and because the resistivity data can be looked at as that sort of pixel or slice at that depth and that location of the survey, and going in from the wall as well from the top of the wall. RICO is most concerned about the performance of the first 10 foot of the strip zone behind the wall, because that's where you can get the most failures. The stresses are all being developed, and it's the greatest concern. So we focused on the first 10 feet, whether it was from the top of the wall next to the pavement in the grassy area that we were able to do the resistivity values along the length of the wall, nominally 850 feet. Then you're looking at the different lines, 1 and 3 are at 3.5 feet, 2 and 4 at 8.5 feet. And line 5 is the top of the MSE wall area, basically the backfill soils, right next to the pavement, about 9 feet behind the wall. So that was a grassy area that was very convenient to spike in the electrodes. So as you look at those percentages, there's not much that was very corrosive, only like less than 0.1%. Around 13% of the total area tested in this 10-foot zone closest to the base of the wall at 3.5 and 8.5 feet up from the base, and including the top of the wall, you can see that it was in a greater amount, particularly going through that. Typically at the base of the wall, it was fairly high as well. So that's not just the icing salts. Those are somewhat the conditions of the soils. The backfill is originally placed. The upper part can be influenced by the de-icing salts, much more so. And then again, moderately corrosive from 2,000 to 3,000 ohm centimeters, predicting anywhere from 16% to 27%. So when we summed all this up of these 7,355 ERT data points, you can see the breakdown of the percentages. So in terms of very corrosive, which is the bottom line in the table, to corrosive to moderately corrosive backfill soils at this time that we measured in the field with the electrical resistivity imaging or electrical resistivity tomography results, you can see that we had about 32% that were in this category. But a lot of that, of course, was in the more moderately corrosive, with some in the corrosive range in doing that. So taking that all together, to boil it down for the project, we summarized it as corrosive to versus moderately corrosive, and the approximate, which is less than 3,000 ohm centimeters, making that the division line, the 30 ohm meters in our data, because that's how the geophysics measures it in ERT, but the engineers in laboratory and material testing use ohm centimeters for design purposes. But it shows it going to 2067 to 2086, which means that, but the yield stress strip section where it would really fail would be 2100 to 2128. So the bottom line was it wasn't, there could be zones of localized severe corrosion based on the backfill soils, but most of it was in corrosive to moderately corrosive, less than 30 ohm centimeters. So overall, although there's cause for concern and obvious failures in the upper part, that it was not in imminent danger of failure and seemed to, it was predicted to have a pretty good remaining service life. So with that, we're about where we thought we'd be. We'll certainly say thank you to everyone for attending today and be happy to answer, Jared or I, any questions you might have. So let me put that slide back up there for a second, if you want to.
Yeah, decided to stop.
I think I hit one slide too many. So we
go all the way through it again.
We can go back to the beginning. Like I say, we will be putting this recording up on our YouTube site. So I will certainly, we want to open it up for the attendees, say thank you very much for attending it and hope you found it useful, but we'd be happy to answer any questions that you might have. So with that, unmic yourself and ask a question. If you want to put it in the chat, we'll look for the chats. There is one in the chat, so we can start with that. Certainly, the question of moisture content comes up. They did sample and got the moisture content for those top soils where they excavated it. We looked at it a little differently in terms of corrosion evaluation. This is the existing conditions. And at those depths, it's kind of the ambient moisture content. Whatever it is, that's the resistivity. We don't think it was saturated by any means. But even so, seeing that it was below the criteria of 3,000 ohm centimeters or 30 ohm meters is the problem that exists in the backfill soils is placed. So I don't think their quality was quite as high as they thought when they placed them originally. Hopefully that helps you in that regard. So, but if you wanted to be extreme, of course, I shouldn't say extreme. If you wanted to be thorough, And forensically, you would have to drill a boring, sample it every 5 feet, say, get the moisture contents, and then take them to the laboratory and do the saturated laboratory test to see how bad the soils could get when fully saturated. Okay. So does anybody else have a question in that? Thanks,
Sure.
Mr. Wood. Yeah, go right ahead.
So kind of on that note, you were dealing with soils here with the MSE wall and kind of using that as a segue into, how fast the steel would corrode. Could you do the same thing in maybe rock? Because we run into all the time. I work in underground mines, and the ground support, right, is all steel. Some of it galvanized, some of it coated, but we have a real problem with corrosion in certain areas, and these drifts span thousands of feet, and so sometimes a certain area, the ground support will become compromised because the ground's so corrosive, but it's rock instead of soil. So I don't know if could you apply this kind of similar technique to something like that?
I think you can. I'll certainly let Jared speak to it as well. You have to be sure you couple the electrodes, which he may comment on a little bit here.
Yeah, I think you can get estimates, and conductivity is of course a very useful, trait to help, correlate and see how bad things actually are. But you would have to know, I feel like you would have to have a little bit more information, like classifying, okay, like in this case, we had a known, okay, 30 ohm meters is sort of the threshold that we're supposed to be looking at. So we would need to have something to correlate with there in order to, specify or classify anything.
Yeah, I would add though that that criteria is pretty broadly accepted for corrosion cases of resistivity in soils. So I think it would extend to rock as well. And it may be your local geology is varying such that there are just simply lower resistivity, higher conductivity rock. As far as coupling it goes, I mean, you're quite used to drilling holes in the rock. The holes would have to be drilled. You can't drive the electrodes in, and you could do them at a bit of an inclination, I think, to keep water in them and fill them with salt water. Is that how we would approach that, simply put?
I think just drilling them would do just fine. And then, yeah, so drill through a foot and then get as deep as you can with it. And yeah, use salt water to help with the initial coupling of it.
I still think thinking about gravity and water running out of the hole, I'd angle them a little bit down so it would hold water.
Sure. That would be fine.
Okay. There's another question.
Thank
It
you.
says, how close were the lab results to the electrical resistivity imaging? They actually compared because when they tested those soils, they found that they were below the criteria also. So you can't say it exactly correlated because they're doing a specific location, but it did support it in that regard. And we commented on that report and reviewed all the other information on the lab tests they did have versus the criteria. Okay.
So
Anybody else have
I
another question?
I have a question. So so if we want to determine the how hard to excavate through the rock, is there a criteria we can use?
For hardness for excavation, I think you would more approach that with a seismic method like refraction in order to generate what's called like a rippability. So you would use a method called seismic refraction tomography for trying to get rippability of rock. I don't think resistivity would help too much with trying to classify what rocks are excavatable.
Oh,
Yeah, we've also, when we take seismic refraction data, we normally take it in such a way we can do multi-channel analysis surface waves analyses in case it happens to be a interlayered, slow, fast velocity system that won't allow refraction to occur. So you can always use, with corrections from shear wave velocity that comes out of normal so-called multi-channel analysis surface waves or MSW surveys, then you would correct with Poisson's ratio and density and get into a compression wave velocity, which is what Caterpillar has done for their rippability charts based on faster velocities for a given size. They have like D8s, D9s, D10s rippability charts for excavation sake. And the faster it is, the harder it is, the higher the modulus is. It's not a perfect correlation, but it's a pretty good indication. And the Caterpillar is the one that's led the way in developing the correlation.
So another question I have, for oil fields, does the electric resistivity help with detecting minerals?
For oil fields, I think the more common use case would be seismic for detecting layers because at that rate you're way deeper into the subsurface. I think resistivity, most surveys are within the top 1,000 feet. With refraction methods and seismic, you can get much deeper. Resistivity has been applied for mineral exploration, although I think there's other methods which could be more useful as well there. Resistivity in our case, we often use just for near surface geophysics, which is, usually within the top 300 feet. But yeah, you would be able to detect, mineral veins or just areas of anomalous higher conductivity, which could correlate with areas of minerals for mineral exploration.
Okay, thank you.
So the recordings will be put up on the website. Probably pretty quickly, but within a week, I would think we'd have it up on the website. There's another question on the chat. Well, the metal reinforcement strips on the ERT. Okay, that's a good question. They certainly are there, but they are sort of uniformly there. So you're still most sensitive to the backfill soils. And because they're not all electrically connected, you end up with a situation where you're really sensitive to the backfill soils and not the electricals, the metal strips.
Yeah, I definitely did worry about having that influence. I think it would have been useful to do a test of regions where there are MSE straps versus where there aren't to see if there's correlations there. But I don't think they would have had too much an effect since they are relatively small compared to the effects of, normally what you would see out in the field.
Yeah, volumetrically, it's quite small. Plus, in an MSE wall, the strips are always going to be there, top to bottom. They vary the density and spacing a little bit, depending on the design and location.
Right.
All right. Uh, how does positioning accuracy of the electrodes impact the results? And what survey method do you use for electrode positions? This was so geometrically similar. I think they were 9.8 feet apart that we just put them right at every joint. And we did have a tape, but taping was adequate in this case.
Yeah, we used the measuring tape, and yeah, the MSE panels were at equal spacing, so that was easy enough to just account for. And then we did use RTK corrected GPS for the top electrodes, and so we changed the distances based on those XY hypotenuse distances for GPS location.
But they still laid out with the tape reasonably accurately, so it wasn't a big impact at all. And with the GPS being within a few centimeters, that was very accurate. Okay. So do we have another question? Thanks to everybody for
Sure.
the questions. Okay.
I have another question. So we've got basically a slag wall, right? So old,
Mhm.
smelted material that was dumped over kind of a slope or a cliff back in the day, and that the contact between the natural ground, right, maybe a soil horizon, and then bedrock, which is likely like a basalt or something. We were originally, proposed doing seismic reflection there. 'Cause, the inversion with the seismic refraction may not show that contact, but the main point of doing this work is to kind of map out the dip and how deep this contact is. We know this wall is about 100 feet, but it varies from, 0 at the top of the slope to 100 feet at the bottom. And we're thinking about doing an ERT survey, but are unsure exactly how the electrical properties of the slag, right, which is kind of molten metal, right, with some extra rock in there. And then that contrast with maybe the native soil and the bedrock. Do you think that ERT surveys may show this contrast relatively well, or if there's going to be enough difference in resistivity there?
So are you looking for the slag contact or a bedrock contact beneath that?
Yeah, so we're mainly looking for the bottom of the slag. Um, and we're unsure exactly what that contact may be. It may be slag on bedrock, right? It kind of could have been like a little bit of a cliff, or it may be slag, some kind of soil that may be altered a little bit when they poured the slag, and then bedrock. So we're not necessarily very concerned about, the contact between the soil and the bedrock, but more of just that bottom of that slag.
So it varies from near the surface to 100 feet deep is what you think?
Yeah.
And over how big an area, roughly?
Oh, it's about 800 feet long, and then the slope is, in the other dimension, the width of it is about, I'd say, 100 feet, 200
And
feet actually.
so how steep does that make the slope? Is it walkable?
So the top of the wall is walkable, but the face of that slag pile or wall, you'd call it, is probably about 45 degrees, 50 degrees, so it's fairly steep.
Yeah, I guess Jared can weigh on this as well. I think ERT can certainly work. I'll let him speak to that directly. Depends on the electrical resistivity contrast, obviously, of the properties of the materials to pick it up. As in anything geophysics, what's the contrast and will the method measure it? I think doing multi-channel analysis surface waves is not a bad approach either because that does deal with if there was a slower velocity soil below the slag over the bedrock, it can pick that up, particularly if it's on the order of 10% thickness change. It's larger to be sensitive. That's the problem with MSWs. You have to have 100 feet deep. You might have trouble discriminating a layer depending on the velocity contrast is what we don't know. It isn't at least 5 foot thick or something to 10 foot. So Jared, what do you want to add to
Yeah,
that?
I mean, resist, of course, it'd be better to do both methods just because they have their own sensitivities to different materials. MASW would do a good job. Reflection has its own issues. I think reflection should be more used for deeper surveys past like 1,000 feet, just because you have the effective ground roll or surface wave information within that very top surface. So we'll be using that surface wave information for MASW.
Yeah, and the one thing about the MSW, as I mentioned earlier, when we do a seismic survey, if refraction works, the data is there and we can look at it. But it depends on, in this case, the slag having a slower velocity than the basalt,
Right, but
and
yeah,
there not being any real topsoil in between.
reflection wise, yeah, that's
Well, refraction. I was actually
yeah, you were talking reflection, but Michael had mentioned trying out reflection.
not likely to work.
Correct, yeah.
It's well, it's so shallow. I shouldn't totally rule it out because if it's basalt, that may not be so much denser and faster than your slag. Do you have any feel for the velocities of those?
No, not currently. It's pretty fractured basalt, we think, but
Mhm.
yeah, we don't have any drill core or anything like that because we'll also drill, core some stuff and correlate that with, either the ERT survey or the seismic survey that we just decide upon. But
Yeah.
yeah, I was just kind of
Mhm.
interested in, the resistivity of the slag, which I'm guessing is going to be pretty conductive, I think. I don't know what your opinion on that is, and
It, it,
then how
mhm.
conductive basalt is.
It probably, just thinking about the survey, and we'd be happy to talk to you about it in detail if you'd like to. But thinking about this, we have land streamers for our seismic surveys. Those could be, of course, it's quite an angle though. That's the problem. Now your geophones aren't going to respond properly. We'd have to the seismic, once they become angled, is a complication because we're not going to easily spike them in, it sounds like. It would take climbers and keeping that vertical. But, and I would
Right.
think the ERT survey should probably be at the same elevation, sort of slicing it into maybe 3 or 4 surveys. What do you think, Jared?
I mean, if it's possible to drill into
Mhm.
the material there, I think it'd be fine to just do a long line.
You probably still have to, at 45 degrees, that's starting to get tough for people without safety ropes and all that to go across and install things. So it can be done is the right answer, but we'd be happy to talk to you about it more if you want to.
Sure, thank you.
Kieran had put a question in the chat asking if the metal if meshes affect the data. It does. just like GPR gets pretty stuck in the any metal meshes just because you have all of your data reflecting off of that metal and not penetrating through to the subsurface. It's a similar idea for resistivity. I think you'd have to have a very dense metal mesh for resistivity to be highly affected, because all that deeper information ultimately is not going to be too much. Uh, yeah, it depends on how dense the metal mesh is, but it does kind of act as like a Faraday cage for your path of least resistance current to go straight through it.
I think in this case, they're generally spread at least a couple feet apart, and further depending on the design of the wall in terms of the metal strips in an MSE wall. So it's just not a big factor. We didn't see anything uniformly indicating we were dominated by the strips, by the way. It definitely varied with the soils because the strips are uniform.
Yeah, the
The-
pseudo section and the results were seemed very normal, as if I was doing a normal survey on grass in a field in the middle of nowhere. It didn't seem to be much effect of metal or dense metal artifacts within the wall.
And for the horizontal ones that are done from the face of the wall, that's limited strips along that exact line, more so than if you think of the mass of strips from top to bottom.
Mhm.
It's a little different, but we didn't see an effect that way. So I think it's a small amount of metal that it's uniform. Whatever effect is there, the soils still are what make the differences. Okay. Well, we're right at the end of our hour. If there aren't any more questions, we sure want to thank all of you for attending. And hope it's a benefit to you. Be happy to help you in a variety of geophysical or non-destructive evaluation needs. And wish everybody a good day.